Welcome to the fifth lecture in this series on neutrons and soft matter science. This is the fifth lecture in this series, and the first of the two I'm going to give. And it's after the introduction by Sunny Sinner, properties of the neutron, and a quick run through of all the soft matter techniques, or at least a subset of them. I'm going to back up a bit and go back to those early view graphs of science. Sort of work through the properties of the neutron with respect to what we have to do to make neutrons available for our instruments, and how we have to build instruments for those neutrons. And so the talk title is obviously Neutron Sources and Instrumentation. So we can go back to the very first real neutron experiment, which I've titled Chadwick Identifies the Neutron. And I call it Identifies the Neutron because the neutron had been turning up for at least 5 years by the time Chadwick did his experiment. And people had been misidentifying it, and it had been expected for over a decade because Rutherford had pointed out that we know the mass of nuclei. We roughly know how big a proton is. We think the nuclei is made up of protons. There's got to be something else in there. They weigh too much, most of those. So, and we needed something to balance the charge, otherwise the nucleus would fall apart. Because positive proton charges would all repel each other. So the neutron wasn't a big surprise, but nobody could find it. And it was turning up, but nobody could work out why. And if we go to the way Chadwick did his experiment, what he discovered, as a few other people have, was that if you have a polonium source emitting alpha particles, put a sheet of beryllium in front of it, this magical, very, very penetrating type of radiation would come out. And if you put an ionization chamber out in the direction of this ionization, you would see, occasionally you would see a little bit of a signal. So it was very, very penetrating. You could actually put pieces of lead in front of it, and you could see that a little bit of ionization. But you wouldn't see very much. But if you put a piece of paraffin in front of it, what you would see is a lot of ionization. And he finally worked out through a bunch of difficult experiments, including putting cloud chambers where that I labeled this ionization chamber here, that what was coming out was protons, and that they were essentially being bounced out by a large neutral particle, which we now know to be a neutron, which had about the same mass as the protons. So the neutron was identified. Chadwick got the 1935 Nobel Prize for Physics. So what do we know about the neutron so far? We know that it's a neutral particle, and we know that it's a little bit weird when it interacts with light atoms, like the paraffin you put between the beryllium and the ionization chamber. And highly penetrating means weakly interacting, which will be a theme which will appear over and over again during this lecture. So thermal Bragg diffraction. Well, that too was pretty obvious. The moment that the neutron was identified, you already knew that diffraction of neutrons to study the way that nuclei were arranged was possible. You knew that nuclei bounced off nuclei somehow, interacted with them somehow. You knew about X-ray diffraction. The Braggs had been doing that for 20 years in 1932. You knew that massive particles had a de Broglie wavelength. That had been done in 1927 by Diffraction. Chadwick determined the neutron mass, so you knew what the wavelengths would be. So a thermal neutron, you knew that the thermal neutron's wavelength would be, as that previous view graph told you, about the same size as an atomic spacing. And in fact, pretty quickly, about 4 years, Mitchell and Powers and Hubble and Pressbrake did a demonstrator experiment of Bragg diffraction of that crystal surface, which was pretty much a carbon copy of what Davis and Gurman had done for electrons. The only problem then is you've got this main idea, but you don't really know what you don't have a source of neutrons. Well, you had the idea of neutron scattering, or at least you had all the pieces, so you would have suspected pretty strongly that it was possible. But you didn't have good sources. For many years, neutron sources they had were just sort of slightly beefed up versions of Chadwick's alpha particles banging into beryllium. And in fact, we still use similar sources, but they're not very good for much except testing neutron detectors. They didn't, at that point, know a lot about the interaction strengths, and they were building up the knowledge on that slowly. And neutron energies and neutron detectors, the neutrons that we're finding were actually a little bit high energy to what they want to actually use for neutron diffraction. And then there was a little thing called World War II, which kind of got in the way, but also answered many of the questions that had been needed to be answered from that previous list. Sources were made available, interaction strengths were measured, neutron energies and neutron detection became a serious wartime problem. And one of the ways to deal with that wartime problem was to build a thing that later became known as, was originally known as the Clinton Pile in Oak Ridge, but it was originally called the Clinton Engineering Works. And we now call it the X-10 reactor, built in 1943. And that after its war work was finished, was taken over by two gentlemen shown in this picture here. Ernie Wallen, kneeling, Cliff Scholl, standing there. And what they did was, Ernie Wallen had worked out that you could do neutron diffraction. So he had borrowed an X-ray machine, or at least the back end of an X-ray machine, from the University of Chicago, in a neutron detector, which we'll talk about later. And he had put this instrument on the pile, basically sitting a little bit lower on this picture of the room, so they'd be a little bit underneath this one. And they'd been sick of the war, and they were desperate, as Cliff Scholl said, to find something useful and happy to do with neutrons. And this is what they found. They found the development of neutron scattering instruments. We need to build a neutron scattering instrument. Well, we need, number one, a source of neutrons. We need a way of selecting the wave vector that goes in, because that's the wavelength, that's the scaling that we're going to apply to the measurement. We need an interesting sample. This is actually a fairly expensive way to do business. And we need a neutron detector and a method to determine how the neutrons that got to our detector, what their wavelength was. If it's an elastic scattering experiment, it will be the same as what we went in with. If it's an inelastic experiment, it will be slightly different. But all we're trying to measure is the neutron scattering function, which is a function of the wave vector change, as defined by Bragg's equation, and the energy change of the neutron. So, let's start at the beginning. Well, maybe not the beginning, I jumped ahead of myself. So in one sense, you can think of neutron scattering instruments as a kind of demonstration of wave-particle duality. So we've got Louis de Broglie up the top there, who said that the momentum of a charge of a massive particle was equal to Planck's constant divided by its wavelength. And that wavelength is the scaling of what we're measuring. And what we have a tendency to do in neutron scattering, nearly always, is think of sample interactions in wavelength terms and think of instrumental terms like which direction the neutron goes and where it winds up on the detector in particle terms as a little lump of something flying through the air. A source of neutrons. Two major ways of doing it for neutron scattering instruments. One, the fairly familiar fission reactor. It's a steady state instrument where basically thermal neutrons hit a heavy nucleus, in this case U-235, which breaks apart, spatters out more neutrons, which have to be cooled down a little bit. Those cool neutrons hit another U-235 instrument nucleus, and the so-called chain reaction goes on. They're continuous. About every time you break up a U-235, you get one neutron. You get about 180 million electron volts per neutron, which is a fair amount of energy. The other method is spallation neutron source, which looks slightly similar. Basically, you take a charged particle, in this case a proton, though you could wang just about anything in there, and you hit it into a heavy nucleus, and you essentially bust it up, and it essentially evaporates out neutrons. There's no chain reaction. You can turn it on and off. So you usually pulse it. So you fire a lot of neutrons, so you get a pulse of a lot of protons at the target, so you get a pulse of neutrons. You get more neutrons per proton than you do from the reactor, and you actually generate less energy per neutron. But they are very, very hot neutrons. So what does a nuclear reactor, this continuous source, look like? Well, the neutrons are produced by fission, usually 230 and 235, as I've already described. You have one little advantage here. To make the fission go, you have to cool these things down with water. So you have to have neutrons that are already slightly cooled down. So you start off with a reactor. And this is the advantage that Charles Mollin had, that already has slightly chilled neutrons that are moving down to where you need them. You get neutrons at more or less a constant rate, and you can get at a reactor like the high flux isotope reactor, which you can see in operation here, that Cherenkov radiation from the reactor in operation. This is the core of the reactor. Basically, the volume of that core, it's essentially a small garbage can size, so it's about 50 litres. Is cooled with water. It has a radius of about 50 centimetres, and if you look at the edge, it's enclosed by a beryllium reflector, and if you look in the edge of that beryllium reflector, you get about 10 to the 15 neutrons per centimetre per second. It's a little bit hotter than you like, but they work quite well. Spallation source. We produce neutrons by nuclear spallation. So the way we do business here is we have an accelerator beam, usually pulsed, though there's no actual requirement to do that. We're going to use the time structure that it generates later. The neutron energies have to be moderated a lot because this is a very high energy process. The neutron beams are of the order of 800 megavolts, or at least the proton beams are of the order of 800 megavolts. And you generate a lot of neutrons, again, in this case about 10 to 16 neutrons per centimetre per second. And they quite often have this form that there's an accelerator, which goes into a compressor accumulator, which basically squeezes the accelerator pulses so they're shorter in time, because we're going to need the time structure. And then after going through the compressor, the neutrons are winged into a target, which is viewed by, which is in this case Mercury. So the characteristics of the sources are pretty much as you see here. The SNS, the spallation source here at Oak Ridge, it has a rep rate of 60 pulses a second, so that's every 16.6 milliseconds you get a pulse. And if you compare the number of neutrons it generates to the number of neutrons that HIFA generates in 1 millisecond, you find they're about the same number. But the next SNS pulse isn't going to be there for another 15 milliseconds or so. Meanwhile, the HIFA is still chugging away. So what this turns into is that roughly the peak flux of the SNS is about 10 times the flux of the HIFA. And the HIFA flux overall is about 15 times the average flux of the SNS. Historically, things have been improving with time. Chadwick's successes improved things by a few orders of magnitude. The development of the reactor rapidly accelerated things over only a few short years. And then things sort of slowed down. This dotted line here is reactor fluxes. You can see that effectively they had peaked technologically in the 70s. There was probably another factor of 3 or maybe 5 in advanced reactor sources that were never built, but the technology is more or less flat at this point. However, starting in the early 70s, the spallation source development started, and after a few fiddles with repurposed high energy accelerators, people learned how to generate neutrons by spallation. And in the late 80s and early 90s, or the early 80s through to the 90s, spallation sources became available. IPMS at Argonne, Lance at Los Alamos, ISIS in the UK, the SNS here now, the last 5 years. The SNS is being upgraded, and the spallation source, which is slightly different to our spallation source, is being built at Lund in Sweden. That's the ESS there. There are also some continuous sources which don't use pulse accelerators, SynQ here and SynQ's upgrade. And JPark is a Japanese spallation source, which is coming online about here on this diagram. Anyway, so at the moment there are about 2 neutron. Oh, the other thing to mention here is that what we're really looking at here is peak neutron fluxes. So these would lose a couple of orders of magnitude. Because the peak neutron flux of a reactor is the neutron flux of a reactor, whereas the peak flux of the spallation source is when pulsing. So, arrow out of the way. So let's have a look at what the neutrons that I talked about already are. Well, the properties we talked about are energy of thermal neutrons. Sunny talked about the energy of thermal neutrons, we often say, are similar to the energy of elementary excitations of solids. True. The wavelength of neutrons is similar to the distance between atoms, also true. Thermal neutron, call it 20 degrees C, the temperature of this room. You go through the math, that's about 25 millielectron volts. And its wavelength is 1.8 angstrom. Good, check, atomic separations. Its velocity is 2200 meters per second. That's about velocity of sound in solids, roughly. The only trouble is when you look at the energy of the neutrons, they're big MeV. So they're both of those sources, particularly the spallation sources, are running very, very hot. So we have to cool the neutrons down. And the way we do that is by something called neutron moderation. Now, of course, neutron moderation is something that the reactors already have to do. So there's water here and a beryllium reflector, and it's cooled, it's maintained at energy, and the neutrons coming out of the core basically bounce around in this reflector. Some of the neutrons bounce into these beam tubes and exit the reactor and meet in neutron instruments outside the reactor vessel. If you want even colder neutrons, what you have to do is arrange for them to interact with something even colder. Right here on the Haifa diagram is a little red dot, and here are moderators that are essentially just buckets of liquid hydrogen. And so the neutrons have already been cooled down a bit, bounce off hydrogen, which they already bounce off a lot, we know, because Chadwick kind of found it out. And they are cooled down to about the temperature of the hydrogen. Now, the hydrogen is about 20 degrees K. This is the Haifa thing. It's only about 4 inches across and sits at the end of the beam tube. Essentially, the neutrons coming this way, or the arrows going the other way. So the energy of a neutron divided by its lambda squared, this is one of these numbers that you can always keep remembering, is 81.82 millielectron volts per angstrom squared. If you look at the flux that comes out of one of these moderators, you will find that it has a peak at about, well, a hydrogen moderator at least, has a peak at about 2 or 3 angstroms. If you go through the calculation that I already did, you'll find that this actually isn't 20 degrees K. Because of the interaction with the moderator, you're always sort of fighting the possibility that the neutron won't actually find its way out. So there's always a trade-off in designing any moderator between getting it cold and getting it out into the beam. So once we've cooled the neutrons down, how do we determine their wave vectors? Well, there's the standard way that we know, familiar with from Bragg diffraction, reflected off a crystal plane. And in this corner here, I have a diagram of a monochromator, which consists of a whole bunch of copper crystals oriented in the same direction, which are basically bouncing a neutron beam off their front faces. And in fact, this is a focusing moderator. They're all sort of slightly canted so that neutrons at various directions will be focused down onto a sample. Another thing used mainly at reactors is the velocity selector, which is essentially a fan for neutrons. And this is pretty easy to work out how this works. When you turn on a fan, air comes through it, comes out of it at a certain speed. It comes out of it at a certain speed because it was going slow. If the air was going through at that speed, or came onto the fan at that speed, it wouldn't touch the blades. And that's what a neutron has to do to get through one of these things, which is essentially a fan. This is built by a bunch called Astrium, who used to be part of Dornier, so they also make jet engines, and it looks actually a lot like the fan of a jet engine. And these are neutron-absorbing blades. And a neutron that, as this blade turns, cannot make it through that fan pitch, is absorbed. And the wavelength that you choose is proportional to the fan pitch by the speed you run the fan. And finally, time of flight, the method most often used at Spallation Sources, where you have a time that is zero, that is when you've generated the neutrons in that Spallation source moderator, running down to a time when it arrived at the detector. Basically just take your known velocity of the neutron, inversely proportional to its wavelength, the time from the spallation pulse until it was detected. And you can read this, so basically for a 5 angstrom neutron, it gets out of the hydrogen moderator, it takes a little, even the slowest neutrons are out in 200 microseconds. Basically that's time for a neutron to go almost no distance. And the times of flights through meters of instruments to go 10 meters of 4 angstrom neutrons takes 10 milliseconds. So these have excellent resolution. So we've got these properties, and we want to apply them to finding out something about matter, soft matter. We finally have the right wavelength because we moderated them. They see the nuclear. They penetrate deeply into matter. They can see elementary magnets, which I haven't mentioned. And this is particularly relevant to us, they are very sensitive to light atoms, or at least their contrast in light atoms is stronger, different to the way X-rays than main competitors. So how does an elastic instrument use a neutron spectrum? Essentially, you have a continuous source marked here, so that would be the reactor. And this just gives out a white beam, and then we run it into one of those velocity selectors. Neil? And now we have a video, which will allow me to draw my breath. So at the front end of a neutron scattering instrument, in this case, SANS machine, we select our neutrons. And the neutrons that we don't select need to be shielded, which is why this whole thing was sitting in the bunker there. So how does that fan operate? Well, here it is, in operation. Eventually there will be a neutron. Most sources produce neutrons faster than this. Oh, yep, it's going too slow, died. Too fast, died. Just right. See, it's Goldilocks. And we continue. So we end up with monochromated neutrons, usually velocity selectors. It depends on the width between the blades. The resolutions are about 5 to 20%. A particular narrow range of neutrons, so our beam is now monochromatic. It interacts with the sample. It scatters off the sample, we catch it in detectors.
There's a question.
Yep.
There's a question.
Oh. Didn't I say? Between 5 and 20%. It depends on the pitch of the design pitch of the fan, but you can also change it a bit by twisting the fan as well, which effectively makes it a tighter fan. So basically, continuous source instruments tend to, elastic instruments tend to use a single wavelength band, and it's a narrow spectral band, and it's only a fraction of the neutrons produced by the source. And here's a typical one of those, the NG7 SANS instrument at NIST, and it's about 40 meters long. The velocity selector sits in a bunker here, the sample position is about halfway, and the detector sits in a large tank. And we will hear more about those in the second lecture, I guess. So how does a time of flight source use the neutron spectrum? Well, a pulse of neutrons is produced. It moves through space, and somebody's got his spectrum wrong. The fast neutrons that are supposed to be red, but today fast neutrons will be blue, get ahead of the slow neutrons. And as that pulse goes through the instrument, it spreads out. So if we measured the time of flight, we would know what these neutrons are doing after they hit the detector, having gone through the sample. So we apply the fact that we know how far the neutrons went, going from the source, the moderator, to the sample, and then bouncing onto the detector. And we know how long they took to do it because we know when that pulse started, we know when we detected the neutron. So we're using a wide spectral band. An example of that instrument is the EQ SANS at the Spallation neutron source. EQ stands for extended Q range. So time of flight uses this wide spectral band. It allows you to, at the same point, use more wavelengths than you would otherwise use. So you can actually grab more range of Q, so there's a measure over more length scales in one shot, which basically means that you get a thing called time of flight gain. Sometimes, often, some people say, that makes up for the lower integrated flux that has so far been achieved on spallation sources. You have a bit of a caveat. You have this thing called frame overlap, that if I start a pulse and then it travels through the instrument, slow neutrons from that pulse could be caught up with by the fast neutrons from the next pulse. So how do I tell whose time of flight I'm measuring? So you have to use some choppers to make sure that the source is sort of closed off or blocked over certain periods. I'll discuss that a little bit later. And you often also need to shield from the unmoderated fast neutron flash that a spallation source produces, because there's a fairly dramatic event when a proton beam hits a heavy metal target. And you get quite a number of gammas, and your detectors tend not to like them very much. So you tend to want to be able to put a piece of heavy metal in the way for a brief period, or bring neutrons around the corner, which I'll also explain later. And to round it out, although most of you will probably never use one of these, this is the classic inelastic neutron scattering instrument, the triple axis spectrometer. Brockhouse developed this in 1955. He shared the Nobel Prize with Cliff Scholl for it in 1994. Only Wallen was dead. And essentially what Brockhouse did was he took the simple diffractometer that Wallen and Scholl had used, and he said, well, okay, the scattered beam, if I want to know its energy, why don't I just do another analysis? And as a result, so I come in with my red Ki neutrons. I come out with the scattered beam. I don't know what the wavelength is. I put an analyzer crystal in there. I tilt it around, and at some distance, at some angle, I get reflected neutrons hitting my detector. And so I know that they have the green wavelength. And so now I can measure both the momentum transfer, the difference between the incident and exiting wave vectors, and I can measure the energy transfer, the difference between the energies of the incident and exiting neutrons. And it looks, because it is monochromatic both ends and 3 axes, the 2 crystals of the axis as a sample, obviously. It looks at a spot in Q and E, which is a little narrow range, but you can scan wherever you want. And I rather like this diagram because somebody's done some scans and he's traveling in one direction in the reciprocal space, and then because it's more interesting, he goes off in another direction. And each of these points was taken at a different setting of the instrument. An inelastic example, how do you do inelastic scattering at a pulse source? Well, you do something not too dissimilar to what we did with the velocity selector. You put a rotating little fan in there, except it tends to be a much faster one called a Fermi chopper and vertical. But what it does is it is open for a time that we know from the time that the source came to the source pulse to the time of the chopper. And it is open. The neutrons that now come through here are monochromated, but we also know when they came through because we are timing them. When they hit the sample, they go through an energy change, and we can use the fact that we still know the time and how far they traveled as a monochromatic neutron, and then how far they traveled as a non-monochromatic neutron to work out the energy and wave vector changes. And these instruments, and this is data from ARCS here at SNS, tend to paper the walls and create rather beautiful, wide-ranging pictures of reciprocal space in scattering vector and energy. And there we'll call it a break, and feel free to type in any questions. Did you ask that question again? It's about 5 to 20% and usually run at about 10%. Okay. No problem. It's very odd series. Okay. So, I know it seems like we're not really making any progress, but we're pretty much back to Chadwick's problem. How do we detect a neutron? This is relatively difficult and kind of embarrassing. Neutrons are really great, really penetrating, have great properties, but they're really penetrating. They go through a lot of things. So to detect a neutron, you actually have to get it to do something. And you would like to have it do something in a small volume because you would like to know where it is really, really well, because that's the resolution of your instrument. But if you look through this graph here, which shows the penetration depth of a representative bunch of electrons in yellow, which don't go very far, way less than a millimeter in matter, X-rays that go a centimeter or less, or millimeters or less. Neutrons basically are starting, many neutrons seem to be able to go through about 5 to 10 centimeters of solid matter without even noticing that it's there. So 37% of neutrons will go through basically about 10 centimeters, 1.4 angstrom neutrons at least, will go through about 10 centimeters of calcium if you had a lump of calcium sitting there. This means you're going to have to be a little clever. Well, we've got some good things here. We notice that some materials, boron here, cadmium, samarium there, and a couple that are isotopic that aren't shown here, actually do seem to be stopping the neutrons in a reasonable distance, basically less than a millimeter. So they are candidates for a detector, provided they do something that we can detect. And a neutron detector is basically something that uses a neutron's interaction with the atomic nucleus to produce something else that we can detect easily. A prompt gamma would be useful or usable, but you've got a problem in that you're operating in a nuclear facility. You've got a vast gamma background. So how do you tell the neutrons that were produced by your interaction with your detector from the neutrons that were just there from the reactor or produced at the spallation source target? The best thing to produce is a charged particle. And here are a list of reactions that have been used for neutron detection, starting with the interaction of neutrons with helium-3, which produces an excited helium-4 nucleus, which promptly breaks up into a proton and a triton in about 3/4 of a megavolt of energy. The only problem with that is that helium-3 is rare. Lithium-6 finally produces a charged helium nucleus and a triton, and 4.8 million electron volts. But there's not quite enough of that, and the cross section is low. Boron, a lot of the time, produces charged lithium-7 moving through the world and interacting and ionizing things, and helium-4, and quite a lot of energy, but also produces some gammas. And one can also use cadmium, gadolinium, and back at U-235, which we already know has a way of interacting with thermal neutrons. These cross sections are isotope specific, so the isotope you use matters. Helium-4 doesn't work, helium-3 works, but it's only a tiny fraction of 1%. Lithium-6 works, it's only less than 10% of normal lithium. Boron-10 works, but it's only 20% of boron. The cross sections are inversely proportional to wavelength. Basically, this is simply a matter of the fact that if I stay in the presence of an absorbing thing longer, I'm more likely to be absorbed. So the absorption cross section is proportional to 1 on the velocity of the neutron, which is proportional to its wavelength, or if you want to think of it in these terms, 1 on the square root of its temperature. And the numbers that are given here are specifically for so-called reactor neutrons, which are 2,200 meters a second, 1.8 angstroms, and 25 electron volts. So these are the reactions that are being used. And I'll just go through a few of the detectors. The overwhelming fraction of the detectors you will probably use, at least early in your career, are helium-3 gas detectors. Essentially, they take helium-3, enriched helium-3, highly enriched helium-3, usually produced by the decay of tritium or from wells that mostly in the US, in which there's some helium trapped geologically. And you put essentially a high pressure of this because you have to need a lot of density of the helium to absorb the neutrons. The cross section isn't that high. So you have put in some 3 to 20 atmospheres of helium in there. And you create something called a proportional counter, which is basically a steel tube or aluminium tube with a wire running down it. You put a charge between the tube and the wire in the center. When a neutron interacts with the helium-3, it produces the charged particles, the proton and the triton, analyzes the gas. The gas sees the voltage you put across it. Basically, the electrons produced by the ionization of the cathode, the positive ions move to the, the electrons move to the anode, the positive ions move to the cathode. You see a pulse of neutrons. They're usually cylindrical, though you can make an area detector by putting many wires in a tank of helium. If you look for the pulse at this end and this end, you can find out that the neutron pulse, or at least the electron pulse, started here, which is within a few millimeters of where the neutron reacted with the helium-3. They're very, very efficient. You can get them up to about 90%. They are very insensitive to gamma rays, which is a very useful thing for neutrons because there are so few neutrons in the world that quite often one of the most important things a neutron detector can do is not detect gamma rays. They have great timing. The pulse that they produce is really short, of the order of a microsecond. So that's good for the spallation neutron source, which is going to need time of flight. And unfortunately, they're almost a thing of the past because recently other requirements on helium-3 and a dearth of production has meant that there's a massive shortage. So people are developing other types of detectors. It is possible that the spallation source being built at Lund, which doesn't need really good wavelength resolution because its instruments, again, it's going to use a much longer pulse than SMS and have instruments much further away from the source, so it doesn't need as good time resolution. We use BF3. BF3 is a fine neutron detection material, but because of a lower cross-section, it takes a longer detector to detect the neutrons, which means it's traveling further through the detector, and you lose energy, you lose timing resolution, or wavelength resolution. So other possibilities exist, and they have their advantages and their disadvantages. Neutron scintillation detectors, essentially you put something that will interact with neutron into a standard scintillator screen that will sparkle if I shine charged particles or gamma ray photons or X-ray photons at it. And usually what is done is that lithium-6 is put into a phosphate, either zinc sulfide, which is opaque, or this GS20 stuff here, which is clear, being laser tested here. And essentially you do exactly what a scintillation detector does. It creates a little spangle of light. And these detectors, basically the scintillator is zinc sulfide. It's here, and it's being viewed by an array, sit in front of this array of photo detectors. And if it sees a sparkle here, this photo multiplier will see a certain amount of signal. This will see a certain amount of signal. This will see a certain amount of signal. It'll sort of triangulate where that neutron must hit the scintillator. And this is a barrage of these things around the topaz instrument, sitting around it in 4 pi here, measuring neutrons diffracted off single crystals. They're a bit gamma sensitive, so you've got to keep them out of the way of the neutron beam. But the neutron beam is coming through here, and these things are all at right angles, so that can be arranged. Another technique which has been used is on the powder diffraction instruments here, is essentially to put lithium-6 into light fibers. So the light fibers, put lithium-6 onto a zinc sulfide screen, and then create a light fiber to collect the light. So this gives you the resolution of fiber in one direction, and not very good resolution in the way. And what they've done is they've crossed those fibers. So when the neutron hits the zinc sulfide screen, it gives off a little bit of light. The top layer of fibers basically see the light, they do a wavelength shift, and then it goes in that direction, so you know it was in this fiber, and then which gives you the resolution in this direction, but you really don't know where it's in this direction, but you have a second layer of fibers underneath it, which gives you not quite as good a resolution in that direction because you've already run through a bunch of fibers which may have scattered the light. And they work quite well. Again, they're a little bit sensitive to gammas, but a little bit better. So you get 5mm resolution along the fibers and about 60 meters across at least in the crossed direction. And they're very fast. Their efficiencies aren't as good as the helium-3, but their resolutions are, at least in one direction, rather better. Can be better. Other ways of doing scintillation detectors, if you're not in a hurry, if you just want to measure where some neutrons went over a long amount of time, you can look at a zinc sulfur screen. The easiest way to do this is seeing it sparkling. You basically look at it with a camera. And I turned this around the wrong way, unfortunately. There's a zinc sulfide screen here. The side has been moved off this this neutron detector. The zinc sulfide screen is hit by a neutron beam which is coming from below. And a camera, which is on the left-hand side here, views the screen through a mirror, because if this camera was looking at the direct neutron beam, it would be extremely unhappy through gammas generated in the camera body. And these have very high resolutions. They turn out, for reasons that I can't quite understand at this point, to be a little bit slower than you'd think. So you can't quite at this stage use them for spallation neutron sources, but I'm pretty sure somebody will be working on a faster CCD readout. You could probably use them on a one-channel basis, but they tend to have ridiculously high resolution, so you're actually getting out more pixels than we actually need. So there's a trade-off between the resolution, the efficiency, the gamma background, and the optics in this case. If you want really high resolution, you're prepared to wait quite a long time, that is hours. You can do very high resolution by using what's called a storage phosphor. And what these things do is that if a charged particle hits them, they store the energy in a defect. And that energy just builds up. And when you want to read them, you say turn off the beam and you hit them with a laser. And the stored energy in the defect is given off and you detect that. So you read these pretty much the way you read a CD. And this is the Imagine instrument. Neutron beams come in here. This detector is essentially a drum with one of these so-called image plates wrapped around the inside of it. It's got extremely high resolution, but it reads extremely slowly. But that's okay because the data take an extremely long time to take, because this is for studying diffraction patterns from tiny little crystals. So it's very hard to get very many neutrons onto a tiny little crystal, and the resolution is necessary. So okay, now we've made a way to detect neutrons.
There's one question about peak flux. What does it mean for neutrons?
Peak flux. Peak flux is all the neutrons that you have that you could call neutrons that you could moderate at a particular time. And the particular time that you choose for neutrons coming out of a reactor is any time at all, because they run at the same power level. Peak flux for a spallation source is pretty much while the pulse is going. So you could say I'm going to integrate it over this amount of time and say it's that many per microsecond. But basically the pulse from a spallation source is a microsecond or so long. The pulse coming out of a moderator is a bit longer than that. So you basically just say, what is the strength of my neutrons at that point? And that turns out, if you average over about the time you're interested in, to be about 10 times what you're getting out of the reactor. Unfortunately, after the pulse is finished, it's over. Okay. Suppose it's an interesting question, actually. I mean, it depends, right? If it's not a moderated neutron and it's a fast neutron that's only a background, do I still count it? I think the answer is no. So it's the peak spectrum of useful neutrons. We'll go for that definition. We'll try to work out a way of measuring it properly later. An aside on neutron shielding and beam shaping. Okay, the neutron's coming out in all directions. You haven't got much control over which direction they're going, but you would like some way of defining which way they go. So they'll hit your sample, and so they won't bounce off something else and then hit your detector. So when you're talking about collimating neutrons, you've got pretty much the same problem that you had for detecting them. You want to have them interact in a relative hurry with the material and create something that you can stop pretty quickly. And in this case, a weak photon is an okay thing because you can stop it with lead, steel, and concrete. And a charged particle is great because you can stop it with a few millimeters of just about anything. And some that have been used don't include helium-3, though the average helium-3 detector makes an excellent beam stop. Lithium-6, boron-10, or boron-10 doped into materials like we use a lot of borated aluminum over at the high throne around here. Sheets of cadmium are also good. Gadolinium is good, except its gamma rays are a little bit hard. So the cross sections again are 1 on V, and you can also usefully, because those cross sections are 1 on V, make slightly better shielding by sandwiching something which will slow the neutrons down, like a sheet of polyethylene. So the neutrons will actually go slower after they've hit that polyethylene because they've bounced some of their energy into it. And then if they meet a sheet of cadmium right behind that, or a sheet of borated aluminium or some lithium, they are much more likely to be absorbed because they are moving slower, have longer wavelengths. And when might I use such an absorber? Well, might use it in just a slit of a certain width. Or one could put that slit into a wheel and spin the wheel, and I would end up with a fast chopper which would be open at a given time, which would allow neutrons that I'd already collimated a little bit to only go through when that slot was in a correct position. Or, if I was worried about frame overlap, I might want to let through a much wider band of neutrons. So I have a thing here called the frame overlap chopper. Basically, this grey area, I assume, is a borated region, and this silver area is just a standing piece of aluminium, and we do this because it's has to spin at relatively high speeds, and it's easier to balance this way. So neutrons can travel through this bit quite well. If they hit this bit, they will be absorbed. And as a result, standard frame overlap chopper operates in a certain way. We have a pulse of neutrons starting here. The neutrons, this is how far they've traveled from the source. This is time going on. They travel, depending on their velocities, further in a given time. If I arrange it that that frame overlap chopper is closed for a certain time, around 0 and up to a certain time, only relatively slow neutrons, these ones, can come through. So I can move to a different frame of neutrons. So I can, this might be sort of from very, very fast neutrons to 8 angstroms, and this might be from 8 angstroms to 16 angstroms. And I can repeat this process over and over by rotating this. This red dot here reflects the fact that very, very fast neutrons are hard to stop. And quite often what one finds in a spallation source is a thing called the T0 chopper, which is a narrow chunk of metal which is thick in the beam direction. So, and that basically stops very, very fast neutrons, which can be stopped by heavy metals, as they are in our spallation detector. Take that bit out. Okay, so one of the things that you're really going to have to know is how many neutrons did I put into it, because absolute normalization actually matters. If you're going to know how many neutrons this signal is relative to that signal, it's important. If you're going to need to know how many neutrons between one step in a scan and the next step, you're going to need to know it. If you're going to know between one reactor and another reactor, it's also a good thing to know. The way to measure that is to measure how many neutrons in a calibrated sort of way would have hit the sample. And the way to do that is to create yourself a low efficiency detector, which you put in front of the sample. Now, actually creating a low efficiency detector is actually pretty easy, because in just about any neutron detector you try to build, it'll turn out to be low efficiency. One of the easiest ways to do it is to take our perfectly acceptable helium-3 technology and not bother to enrich the helium-3 very much. Instantly, instead of something which can detect 90% of the neutrons, you've got something that is now full of helium-4 mainly and has only a fraction of a percent of helium-3. So instantly your efficiency has gone down to about 1 part in 10 to the 6th, which is good because you just want to know, you want to catch a fraction of the neutrons in the main beam, and you want to know how many there were, and you don't want to stop too many of the neutrons going through. Another reaction which can be used is this one here. It's basically the interaction of a neutron with nitrogen-14. And it's not done very often, but I thought I'd introduce it here because if any of you have done a radiation safety course at a reactor, you might have wondered, why is the quality factor of neutrons that interact so poorly bad. And they will tell you that, yeah, it's because the neutrons moderate in your body, they interact with the hydrogen and they slow down. Okay, well, who cares? They're slowing down, what are they going to do? What they're going to do is interact with the nitrogen-14 in your DNA and your proteins and give them a very bad day indeed. So that's why the quality factor for neutrons is high. Usefully, just because this is a low cross-section reaction, although about 1,000 times higher than the reactions for other parts which your body is made, you can create quite an inefficient detector with them using essentially the same technology. You can also use a helium, a thing called a fission counter, which basically uses the charged particles from the U-235 nucleus. And you can see that they developed those because they have plenty of it sitting around at reactors, although we're tending to phase them out now. And a reactor is stable to about 1%, but different reactors have different powers. Accelerators operate in a slightly spottier power range. They tend to oscillate by about 10%. This is the power level diagram of the SMS. And you'll see that occasionally it went off. Bad luck if you're doing the scan while it's off. Unless you have a monitor. If you have a monitor, you can normalize your detector. Another thing to notice about these detectors is you still want to create a detector that's good at detecting neutrons because you are up front in the instrument, in the main beam, and you probably don't want to see all the gammas that are being generated, some of which will be generated in the sample. So, a couple of asides and a couple of extra bits. Neutrons can go a long way in air. This is a great thing. This means that you don't have to worry too much about getting them to go about a meter or so. 10% loss for a 4 angstrom neutron, which is a typical Calder wavelength neutron. A long flight path and get lost tubes do require vacuums because you don't want neutrons scattering. You might be measuring a relatively weak signal. You don't want neutrons scattering out. If you're going 10 meters, probably want to evacuate the flight path. Windows are easy because neutrons are highly penetrating. Aluminium, quartz, sapphire, and silicon all have good thermal neutron transmission. If you use quartz, sapphire, or silicon crystals, you don't have to worry about Bragg scattering. Diamond would also be tremendous, and it's increasingly becoming affordable. I have friends who are thinking about designing at least diamond sample cells, or possibly diamond windows in their instruments. Yeah, they can dream. And if we want to go a little bit further, and the other we can transport neutrons because we want them to stop diverging. We don't want them to be affected by inverse square. We can build a thing called a neutron guide. A neutron guide uses that total external reflection of neutrons from a flat mirror that Sonny talked about when he was talking about reflectivity 2 lectures ago. And essentially creates what is effectively a light pipe for neutrons. So essentially, neutrons basically reflect at low angles along this pipe and are transported more or less without loss, provided they are under the critical angle for total external reflection and you evacuate this pipe. And you can make those mirrors rather better. This would be a standard sort of nickel mirror by putting cleverly designed multi-layers on top of that substrate, which each multi-layer reflects a narrow band of neutrons. If you vary those wavelengths, at least those periods, you can actually create something which reflects out to angles of about, nickel reflects, the total critical angle for nickel is about 0.1 degree or 1 angstrom neutron. These super mirrors, as they're called, basically work, and you're given an M value, and that's how many times better they are than nickel. And the best they make, although they're a little bit further than this is shown, are about 7 times as good as this. So basically you get a very strong reflection of up to 0.7 degrees per angstrom. And so you can create quite a divergent beam pi to carry neutrons tens of meters. And you can, in fact, even turn the neutrons around a corner by bending these pipes. The radius through which you can turn them is basically of the order of twice the width of the light pipe by the critical angle of the light, divided by the critical angle of the light pipe squared. And what you tend to find in curved guides is they divide them up into septa, so they can be bent round fast. So these things can be used to transport neutrons tens of meters away from the reactor, which is a good thing because there isn't much room around the center of a reactor or a spallation source. There's certainly a lot of background. I'm going to sort of digress a little here and not go into it, and I'm just going to flash through it, but that's okay because Chuck Marjak will give you a detailed lecture on this. I'm just going to mention neutron spin because it's another way and another handle we have on neutrons. The neutron is basically, as one of those properties back in the beginning of my lecture in Sonny's lecture told you, is a little spinning magnet. And this means that it can be polarized. That little spinning magnet can be pointed in a direction. And Chuck Marjak is going to talk to you about polarized neutrons and mirrors and interfacial reflectivity a few lectures hence. But the things that can be done is that you can modify that supermirror in such a way that a neutron with its spin up and its magnetic field up sees a layer of non-magnetic material and ferromagnetic material as a sort of supermirror. And you can change the thing just as the supermirror on the previous slide did. But a spin-down neutron, which interacts differently to that direction of the neutron. It has a different energy, it's mu dot B, the dot product. So it essentially sees nothing. So it doesn't get reflected by anything except the substrate. Whereas the spin-up neutron is reflected very, very well. So if you operate one of these so-called Meso-supermirrors at an angle between the critical angle for the substrate and the critical angle for how well the supermirror meets, all the neutrons coming out in this region would be polarized spin-up. You can also do the crystal version of this. Atomic spins can be ordered in a similar way so that essentially in one case the nuclear interactions of the nucleus and the atomic interactions with the magnetic field that the neutron sees produces a strong periodic structure, and for one spin of neutrons, and no periodic structure for the other spin, so you reflect polarized neutrons. You can also polarize helium-3 because only one spin direction of helium-3 actually did the absorbing. So if you can work out a way to make all the helium-3 spins sit in the same direction, only one brand of neutrons will get through it. This is a complicated technique that I won't go into any detail. And once you've got the neutron spinning, it can process like a little top in a magnetic field. And so if it's going in a direction you don't like and you want to turn it upside down, you put it into a magnetic field that is perpendicular to its direction and you can turn it upside down. And one of the things you can notice right about now is in the middle of this field region, this neutron is turning around. It came in spin up, it went out spin down, and what it did as it went through this is it turned pi degrees. Which leads us to the other thing you can do to time neutrons if you can measure their polarization, which you can do with supermirrors. Essentially, neutrons, a neutron traveling through a magnetic field region, its polarization will precess around that magnetic field region. The phase of the neutron moving through that magnetic field region can operate as a little clock. That precession of polarization is a little clock that you can use, a third way of timing how fast a neutron went through the material. Because you know the magnetic field, you know how fast it's going around, and with a little bit of cleverness, which will be dealt with in great detail by Dieter Reactor in his neutron spin echo, you can use this to make an exceptionally sensitive energy clock. even more recently, we found out ways, because sending neutrons through canted fields, you can use this to measure angular deviations, and you can turn into a very sensitive scattering machine at low angles. Sample environment. The quick word on neutron scattering sample environment is you can have just about anything you want. Windows are easy. You can go through a large amount of the crystal if you have to. So if you want to build a high pressure cell, you can put a big crystal on it. This isn't a high pressure cell. This is a cell I used for years to measure reflectometry from organizations of solutions underneath a block of quartz. And to do these measurements, the neutron had to go through 7 centimeters of quartz, which it did quite happily with an absorption of only about 25%. Because neutrons go well through air, you can have a meter of sample environment area quite easily on most instruments if you absolutely need it. And this is the sample position of a modern neutron scattering small angle spectrometer built a few years ago in Australia, and it's about a meter from this end of the guide tube to the start of the tube with the detector in it. And this is the standard sample environment on it. But if you want to put a big cryogenic magnet on it, you have plenty of room for it in ancillaries. If you want to put a rotating rheometer on it, you can also do it. There's plenty of room for that. And the neutrons will go through quite a lot of material. And you can study whatever is in the middle. Okay. This is kind of where it all goes a little bit irritating. It's a thing called Liouville's theorem. And it has a formal expression which basically says the phase-space density of non-interacting particles cannot be increased by conservative forces. And seeing it's very hard to do anything to neutrons. You can't squeeze them up, grab them, or push them together. You can't actually sort of collect them and really bottle them up all that well. They are flying, and they're going to continue to fly. What this really means in our case is to increase the phase-space intensity, or the phase-space density of neutrons, and that's really what's hitting our sample. Almost our only option is to increase the volume of the sample, which is kind of okay, except for two things. If you increase the volume of the sample, where your neutron came from becomes more problematic. If you need to measure, because it came from over the area of the sample is big, I can't tell if the neutron came from here or here, I don't know where it ended up. And since we're talking about small, soft matter, generally large structures, what this means is we have a tendency to be talking about highly parallel beams. Highly parallel beams because we want high angular resolution. We could condense, but we lose the angular resolution. So we tend to be dealing with large samples. The bottom line on this is it costs flux to increase resolution, and it costs resolution to increase flux. But if you need the flux and the resolution, you better have a big sample. It's a thermodynamic limit, so things you can do to get around it will usually not work quite as well as you'd like. So what's a neutron scattering instrument? So basically it's a range of choices on how I put the neutrons into the sample. I choose a wavelength, I choose a moderator, I choose ambient neutrons just basically coming out of the reactor. Do I cool them down? Do I run them through a hot source? Sometimes we want hotter wavelengths than are available from the moderator of a reactor. Can I use a wavelength band? I can use a wavelength band on a quasi-Lowry machine because if I hit a crystal, basically the wavelengths that meet Bragg conditions will turn up on the detector. Is it pulse? Do I have a wavelength frame? Did I polarize that thing? Okay, the sample, did alignment matter? Is it a crystal? Is it a multi-layer? Doesn't it matter? It's a powder, it's a liquid, solution or a gas. What length scale am I interested in? What energy scale? What scattering, power transmission, etc.? What structure am I going for? Am I going for structure or am I going for dynamics? Do I have to measure a wavelength or a range of wavelengths? Do I care about the energy? How am I going to care about the energy? Am I going to do it with a chopper to make sure to find out what energy it exited with? Can I do it with a Bragg crystal to take energy? Do I need high resolution? Do I need low resolution? In energy or structurally? Do I analyze its polarization? Did it have interaction with the atomic rate arrangement of atomic spins in material and get bounced in another direction? And so every time I answer that question, I'm fighting a little bit. And so, whoa, and now it totally disappeared. Turns out, and I'll paint a picture in words, is that once you design an instrument, it tends to work, an elastic instrument tends to work over about 3 orders of magnitude. If you build a detector, you put in helium-3 tubes. You buy 100 tubes. There's an order of magnitude, 2 orders of magnitude in angles that you can measure. You might be able to change your wavelength by an order of magnitude. You might use 4 angstrom neutrons and then like 20 angstrom neutrons. So basically, instruments cover a range of range of Q that turns out to be about 3 orders of magnitude. But the instruments you build need to cover about 8 orders of magnitude, 12. So there are a lot of them because there are a lot of compromises to be made. Same with inelastic instruments. They have this same in the direction of structural size. What Q range I look at, they tend to measure 2 or 3 orders of magnitude. In energy ranges, they tend to measure 4 or 5 orders of magnitude. But again, what is suitable, this neutron spin echo in green, for the diffusion of large molecules or membranes is not what we're interested in a hydrogen atom bouncing around inside a storage material, which has to be looked at with a triple axis or backscattering spectrum. So we do neutron scattering all over the world at a relatively small number of places. And they're big facilities. This is the answer to the question of why your proposal got rejected. And they cost $1 or $2 billion. And you get to turn up for a couple of days and measure your neutron scattering experiment. And in pure flux terms, it's not much better than a rotating anode or a benchtop source. So the corollary of this is it would be a good idea if you can learn anything about it by another means, it is a good idea to do that. So know as much as you can about your sample before you come. So why did you come? You came because you know a lot about this sample, but you come with a question that only neutrons can answer. And hopefully over the next, well, Sunny's lectures give you a hint, hopefully over the next series you'll have a better idea of those questions that only neutrons can answer and how they can answer. So, this, by the way, is that diagram that disappeared before, which you probably can't read anymore. But this leads, these different requirements of the instruments lead to a wide range of instruments covering a wide range of length scales and length and energy scales, creating quite a crowd around a reactor like HIFA or a spallation source like SMS. And the similar sensor suites of instruments at a rare number of places, but all around the world. At NIST, Gaithersburg, Institut L'Horloge in France, ICES in the UK, Lance at Los Alamos. And you can read the rest of them off that diagram I showed you before. And why do we use them? Because you get them from the information you couldn't get any other way. Because they have those properties, they are sensitive to those things, because you can make certain features of things light up because they can see things that no other probe you've got can actually see, certainly on a microscopic level. And I also like to stick in a fourth property because scattering is inherently statistical. Come to do neutron scattering because if a picture is worth 1,000 words, a scattering pattern is worth 1,000 pictures. Hopefully I'll make some of that real in my next lecture on neutron scattering. I'd like to acknowledge everybody I stole material from. Sometimes I actually stole material back from stuff that I wrote.
So they all understand.
They all understand everything. No, it's the instrumentation, it's source talk. It's intrinsically boring. And when you see Liouville's theorem, you think, I'm just going to give up.
You guys have any questions?
You can ask questions too, guys. Yeah.
Much.
It's an old experience.
Thanks, Bill.